Hi everyone, just give me 1 second here. There we go. How you guys doing? Welcome to the Math Spellbook livestream. I'm your host Peter, and basically we are going to get into some vectors today. Hopefully you guys are doing well today. Happy Monday. Hopefully your Monday is going pretty well for you guys. Hopefully you started the Monday on a good note. So anyway, let us get into, so I found this book. It was a recommendation I found on YouTube, obviously. I love like watching people that are studying math and physics. I love when they basically do book recommendations. And when they do book recommendations, I end up asking the question, is there an online one? Can I find it? And luckily I found this one. So I think the requirements for this book is that you need to know at least linear algebra in addition to some multivariable calculus. So you guys in the chat, I know many of you are brilliant people within those particular subjects, so if I get lost or if I get stuck in the weeds, maybe you guys will help enlighten me on what I'm missing. But yeah, I liked actually the title of this book, Covariant Physics from Classical Mechanics to General Relativity and Beyond. So I think this will be a really interesting book because according to, I don't remember the YouTuber's name that recommended this book, but this is a book I have not seen before, and it's actually a book that I kind of been looking for because I've been kind of confused about covariant and quadravariant vectors for a long time. Hey Sascha, how's it going? What's the best part of your day so far, my friend? Yeah, I decided not to use my VTube model, just to basically, just try, just basically get the camera out. And also forewarning guys, if my internet cuts out, that's a possibility of happening because, it's changing from cold to hot weather or seasons. So sometimes my internet fluctuates. So that's a forewarning. I'm still I don't really have really great internet. So just let you guys know in advance. we have the real model. Well, you know, at least I had my haircut done, because actually, like, last week I didn't have my haircut until like last Thursday. So luckily I managed to get my haircut done. So anyway, I probably should start the study clock. Your background looks nice. Are you using a green screen? No, I'm actually using NVIDIA Broadcast to give this space background here. Actually, I like the way it looks because I thought it would look more fake, but like, you know, when I move my finger around it, yeah, you can tell. But at the same time, it's like if I don't like put my hands up or do too many crazy movements, it looks like it's literally a green screen, which I think is pretty cool. Okay, so let's get into it, shall we? And Sasha, since you are doing your masters, you probably can offer me assistance if I need it. But yeah, the contour looks quite clean. Yeah, it does. It does. I think it was also my choice of the background as well, because it doesn't look too obvious, and it's a video. It's kind of like a video loop. Let's see. Geometry has two great treasures. One is the theorem of Pythagoras, and the other is the division of a line into extreme and mean ratio. I wonder what that means. The first we may compare to compare a measure of gold. The second we may name a precious jewel. Okay, Kepler. Quite a poet there. Okay. So basically, let's see, coordinate covariance is defined as the invariant of the laws of physics under change of coordinate systems, whether they differ from each other by translation, rotation, or both. Okay, so what do we learn in this chapter? In this chapter, we shall begin introducing various 2- and 3-dimensional coordinate systems, usually used in problems of physics and engineering. Some of these should be quite familiar to the reader, while others may be completely new. Okay. Okay, here's the specifics. Specifically highlight the concepts of line elements, also known as the metric. Okay, I've heard of the metric before, although I don't know the exact mathematical definition of it. As a defining principle of coordinate systems, as well as unifying theme among them. Okay, I'm not going to read all the fluff here. I'm just basically trying to look for the important details here. I guess this is researcher mode. Let's see, in principle, blah, 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 situation of the metric. Next, we will turn to the basics of vector mathematics and discuss their formulations and new language simply known as the index. Okay, yeah. I remember reading this in the other book I have here, which is A Student's Guide to Vectors and Tensors. Actually, I will just open up the chapter for covariant and quadravariant variable vectors, just so that I can actually just get there faster. Furthermore, the notation provides the majority of mathematical material, and so what I know, I probably should start off with what I know about these things. So what I remember is that I remember with like certain vectors, like if you had a vector here, you can have like basically beta, and then we'll just put gamma here just to be simple, and then k here. So this is the basic setup for a vector. So what I've learned about quadravariant and covariant vectors, I think co is basically the lower part, the lower subscript, while quadravariant, like I'm forgetting the pronunciation. Covariant is with the superscript, like Because usually we would usually use, I think, quadravariant, and then like when it's covariant, it's written differently. So it's the same vector but written in different coordinates. So we'll just put that I prime, J prime, and K prime. And I think I saw something within the student guidebook about it, so there was like a formulation that I saw in here that actually makes it a little bit more clear about how it's set up. I think I passed it, did I? No, I don't think so. Oh, here we go. I wonder if I can copy and paste this. I don't think I can. No, I can't. I can't highlight it. Yeah, because, like, according to this, in order to transform it, so here we would have the new coordinates for the same vector, so we'll just put V up there. And then basically we have the, I think in the book they said it as the inverse transform. And I'll just write here, based on, oops, that doesn't look good. So, based on the original, my handwriting is just so sloppy. Based on the original coordinate system, and then you multiply that by original coordinates. Coordinates of the vector v. Vector v is always going to be the same, but it's just going to change coordinate systems. And that's basically what I've learned thus far about them, but I don't know the full details. I think this is what you see in linear algebra a lot, because it's like involves linear, how should I say, linear transformations. That's weird. I'm trying to move up and down, but it's not letting me, so maybe I have to reopen this. Okay, we got the hand here. Come on, load up, load up. Yes, all of this is the idea of tensors. What is going on with my stuff? That's funny. My thing doesn't want to load up for some reason. Let's see if we can try another one here. Okay, there we go. I was like, what's wrong with this? Okay, let's see if we can try opening the original one. I don't know. This one. This one. Wow. Yes, of all of this idea of tensor is just linear algebra at the end of days. Funny. Okay, there we go. But it's not. Why is it? Oh, is it because? Why is my mouse? Why is it not cooperating with me? I mean, can I still write? Yeah, I can still write. Okay, that's just weird. Yeah, my writing software is like not cooperating with me. Because I can't move up or down. Maybe we can just zoom out. No, that makes it too small. push comes to shove, we'll probably use... Let me see. Probably try to use the other thing we have here. Let's see. Now I gotta remember how this program works. And okay, it's the lowest one. So we have vectors. Okay, there we go. So let's recopy our notes. So we'll just write this as quadrivariant. Oh no, quadricovariant. I think that's what it's called. Quadrivariant. Okay, I was right. Okay, never mind. Quadrivariant. And I think like when they teach you math, like at the beginning with algebra and you know, geometry, I think they start teaching you these type of coordinates with vectors. But then we also have to learn covariant. And we'll just put a prime on top. We'll just put a little prime on top to basically signify the difference. And then the transformations. So vector coordinates. We'll just write new here. And then inverse transformation. Inverse transformation matrix. And we'll write based on the original to the new coordinate system. Hopefully I'm formulating my thoughts clear enough for you guys. Vector... Oh, I probably should move this. Now how do I move to the side? Oh yeah, I just have to click this. Oh, I just have to click, okay. Maybe I should use this from now on. Actually, my handwriting looks much better in this one. Vector coordinates. Well, I should probably write OG. That might make it a little bit better. OG. Original. Okay. Oh, oops. Didn't mean to do that. Just drag it like that. Okay. Let's continue on with this. This notation by itself connects vectors and two coordinate systems they define. Furthermore, notation. The thing I like about this book is that it introduces the mathematics like into like higher variables, but at the same time it doesn't Oh, here we go. In fact, I claim that a first two chapters by itself constitute at least 80% of the mathematics needed to study both theory of relativity. As the reader will see, none of this mathematics is far beyond ordinary algebra and a bit of multivariable calculus. Okay, that's what I like. That's what I like about this book, because I heard from the YouTuber that introduced this book, they basically said this exact thing here. So I do know a little bit about multivariable calculus. I just don't know I just haven't taken a full course on it. Like, I'm familiar with some concepts. Familiar. When I say familiar, I mean I kind of saw a definition about it and stuff. And if we see something that we don't get, we'll probably just do problems involving that said thing. Let's see, for the purpose of science, it's commonly used the Cartesian, right? Euclidean geometry and the ordinary geometry that we all study in school, right? Yeah, I love how the author basically kind of says that this is the stuff that you're familiar with. Now let's basically just ease into this. Clarify. Okay. This is a question I've always been asking too about this. Let's say if one happens to be interested in curved or non-Euclidean geometries, like cartographers doing geometry on the surface of a spherical globe, then not only do Cartesian coordinates stop making sense, but they actually become impossible to define, except approximately on the small scale, very small scales. To clarify this, consider the surface of the planet Earth as an example. Assume a perfect sphere. One can draw a straight line in a grid on the floor, in the room, or in the street without trouble. But if you want to draw a straight line between cities, countries, or even continents, you find that you cannot do so and are forced to work with circles, like those with latitude and longitude. In a sense, then, most curved surfaces of interest are approximately flat on a small scale. One says that they are locally flat as opposed to globally. So basically, local means it's going to be a small portion of the space, while globally is the whole space. If I'm phrasing that wrong, let me know if I am. Okay, so we have the right-handed coordinate system and the left-handed coordinate system, and I'm thinking we're going to use the right-handed because of the right-hand rule. Traditionally, we use symbols X, Y, and Z to denote the three Cartesian axes in three-dimensional space, right? So-called right-handed system. So the left-handed system. So if this is because with right hand, you have to move your fingers towards the angle that you're going to. So I'm guessing this would be you guys can't see it, but I'll just raise my hand up a little bit. So this is my right hand, and I'm guessing that with the right-handed rule, you have to curl your fingers towards the angle. So with the left hand, because right now I'm trying to think about which one is the x-axis and which is the y-axis. I'm guessing that basically when you do the right hand, it's basically you're going towards the y-axis. With the left hand, if y is... Because x is pointing out more in this type of direction in the book. So I'm wondering actually how you would do a left-handed rule, if that's even possible. Oh no, I'm looking at the right-handed coordinates. So you stick your hand out, do this with the right hand, and then if it's like this, Maybe, like, when you move your fingers, it's not really about the coordinates. It's really about, like, the direction, mainly. Maybe that's what it is. It kind of shows you that, like, even though I know what the right-hand system is, I probably don't fully understand exactly, like, why is it that is. Let's see, right-handedness conversion. A convention is particularly useful in physics, but index pointing towards... Okay, so the index... I'm guessing you're saying the index finger is pointing towards the x-axis, major along the way the y-axis, and your thumb is pointing towards the z-axis, right? You're using the wrong right-hand rule. Well, this is my right hand. Like, I know, like, from your guys' point of view, it looks like I'm using my left hand. Like, the thing of it is that I'm trying to understand, like, well, how it would work if you used your left hand in this case. Your thumb is pointing towards the z-axis. Okay, yeah, I read that right. Okay. Yeah, I know the thumb is supposed to point towards where the cross product is of that particular direction that the force is going into. But it looks like you're using the right hand rule for curve. Oh, for curl. I mean, I'm basically telling you what I'm familiar with the right-hand rule, because I know when you use the right-hand rule, you have to, like, curve your fingers towards, like, where it's going. Let's see. I sent you a picture on Discord. Yeah, you can post it on the stream materials text chat. So basically, this is what Sash just sent. Oop. Yeah, if you guys have material that you want to send me, like pictures or visuals, just put in the stream material chat. Like right here. Yeah. So this is what Sash just sent. Okay, so this is the... Oh, okay. Yeah, I forgot about this one. Yeah, this is also something that I've seen. So for left hand, if you do the left-handed rule, then that would mean that I'm guessing the index is Y and the middle finger is the X coordinate. You're using your finger as the axis. Don't curl them. Okay. Let's see. So when do you actually use this particular rule? Like for the right-hand rule, then? Is it just basically to oh no, maybe I'm using this for the cross product. Because I remember seeing like physics professors, they would do this to talk about the was it like torque? Not torque. Is it torque? It's basically like when you're doing a screwdriver, and you're basically just like trying to see which force is being applied when you like basically turn at a certain angle. Usually for knowing the direction of the current induced by an electric. Yeah, I heard about that. Yeah, or the other way around. Yeah. So the index finger is the x-axis, and the... Okay, and so on. Or the other way, okay. Interesting. Thank you, Sasha, for, like, educating us on that. Let's see, coordinate systems are defined by the geographic shape that they seem to trace. So the case of, Cartesian coordinate surface of a constant x and y and z are infinite flat planes, as shown in Figure 2. Looks like a building, huh? Like, probably reminds you of like those like apartment complexes, or maybe like a cubicle. Oh, here we go. We have something about access to indices. Let's see now. The conventional twist, blah, 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 blah. However, a more useful notation, and one that we might as well start using right away, employs indices to denote different axes. Or axes, yeah, axes. So x becomes x1, the first axis, y becomes the second axis, x2, and then z becomes x3, where the reader is warned not to confuse the indices with powers. I think we've heard that many times whenever we read books like about this. Unfortunately for all, these are called right hand. Yeah, like, I was just curious about, like, you know, because, like, you could do it with your left hand, but I think it's even harder to do that. So that's why they call it the right hand rule most of the time. Because I think you have to, like, actually do it in a different direction. You're gonna be twisting your arms around. Let's see. It's not x squared, but pronounce x2 similarly to x1, x3. Gotcha. We wish to denote exploitation, then we simply use parentheses to... Okay, so that's good to know. If there is a possibility of confusion, we will temporarily go back to the old XYZ system, depending on the context, okay? This numbering system is known as index notation, okay? Or the component notation. As much more powerful choice than the conventional way, of a variety of reasons that we will see. Yeah, because then you run out of letters and you run out of numbers. Might as well just stick with one variable and just put like a number like on top or on the bottom, depending upon which subscript or superscript you use. The left-handed rule is the inverse of orientation of your vector of space. In order to map your left hand to your right hand to your left hand, you would need a reflection. Oh, okay. Next most commonly used system of coordinates in 3 dimensions is cylindrical coordinates. I remember covering these a bit. I think they're much easier to remember because they follow the polar coordinate system. Because it's a cylinder and not really like a sphere. When it's a sphere, I think they basically use like both sine and cosine, or sine, depending upon which coordinate you're going for. Yeah, here we go. So I'm guessing rho here is supposed to be the radius of the cylinder in this case, because z is still the same because that's supposed to be the height of the cylinder. And then we got the radius, which is rho here, rho squared, and then we got the angle. So I'm guessing these are supposed to be like changing from the coordinate systems. So basically based on the Cartesian coordinate system, from cylindrical to Cartesian, and this one is supposed to be from Cartesian to cylindrical. In linear algebra, an orientation is equivalent to a choice of the determinant. So it depends on the diagonals, then. Well, not really. Not what I meant to mean. That's not what I mean, but like I remember like basically like the determinant is basically you from a 2x2 matrix. I remember it's basically you cross them and you basically do like the product of the I guess like the crosses, and then you minus them from each other. I'll write it down. No, we're not using this anymore. I forgot to close this. What was that? Yeah, because I remember like with the determinant, if it's like 2x2, like A, B, C, and D, it's like AD minus BC. And I remember the determinant is supposed to be the area of I believe it's the area of the space that the matrices is supposed to encapsulate. If I'm wrong, like let me know what I'm missing there. Okay, easy way to confirm. So yeah, so here we go. Yeah, so it is the radius from here. I mean, if this was a cylinder, actually, it's like hard to see with this picture. Oh, they're giving it to us on the like the 2D perspective. An important difference between cylindrical as well as two-dimensional polar Cartesian systems is that the cylindrical system does not cover all of the three-dimensional space. What this means is that while any point in space can be described by a specific set of numbers in Cartesian coordinates, in the cylindrical coordinate system, there is a single point out of an infinity of points in space that cannot be described by a unique set of three numbers. So if you have two bases, you say they have the same orientation if the matrix associate with the change of bases. You have two bases, okay. You say that they have the same orientation if the matrix associated with the change of basis has a positive determinant. What? So there are two bases. I'm guessing like the original and the new bases. You say they have the same orientation. Okay, orientation. If the matrix associated with the change of basis has a positive determinant. Okay. So, same orientation. I'm trying to remember, like visualize what that is trying to tell me here. So, how do we mathematically define the orientation? Whenever you have two bases, you can create a change of bases matrix, right? Because I'm guessing the orientation is just the way the coordinate systems are set up, right? But they have the same orientation, in this case the same setup, if the determinant is positive for the change of basis transformation matrix. Like what I mean is say this part is gives a positive determinant. Is that what you're saying, Sasha? Every vector space has two possible orientations. We're learning a lot today, guys. We're learning a lot today. Thank you, Sasha, for educating us on that. And I'm pretty sure there'll be much more you will instruct us along the way. I don't know if we're gonna do any problems today, guys, because like I just kind of got curious about this subject, and I feel like I'm gonna be like reading and try to formulate my thoughts out loud. So if you guys are studying the same subject, hopefully my thoughts kind of like allow you to get into the the mode of actually like trying to go through the weeds with me. Let's see here. Okay, where was I? Oh yeah, here we go, right here. Let's see, in coordinates, there's a single point out of infinity of points that cannot be described by a unique set of 3 numbers. Okay, this is the point located exactly at the origin of the coordinates, which we usually denote as O. While the coordinates of O in the coordinate system is simply 0, 0, 0, in cylindrical system, only rho equal to 0 and z equal to 0 can be defined, but phi remains ambiguous because any value can be used for it. In other words, there is no unique set of 3. So, if this is 0, and z is 0, is it because it's a single point? That's why phi is ambiguous? Because there's no line to basically dictate what angle it's at? Because I thought... Oh, wait. Yeah, I'm wondering why... I wonder why phi is not also 0. But then again, like, I'm thinking about, in comparison to, angles, because I'm guessing, like, if there is no radius, then basically there's no line or no vector. Hence, there's no, angle there. But at the same time, the angle could be, how should I say? Because I think when we think about like the angle between like an axis, we usually think of a vector that's basically like going up above, like up like at a certain degree when it comes to the angle. But since practically we don't have a radius rho in this case, it's 0, and if z is at the 0 coordinate, then basically comparing the two. No, because, I mean, there is an angle from the z-axis to rho in the two-dimensional case. Let's see. In other words, there's no unique 3 numbers that describe the location of O. The set of numbers... Rho is equal to... does apply to the origin, but so do the... Oh, okay, so it doesn't matter what rho is, because the thing of it is that, like, any angle will describe the origin. Interesting. Okay. So practically, like, rho could practically be any angle, because there is literally, like, no length to, rho. I mean, phi can take on any angle. I mean, rho is basically still 0, so it's not really like a length. So basically, like, phi could be any angle to basically like take on the stance of z being 0. Okay, that makes sense, because it's just a dot. It's not really like a radius. There are an infinite number of possibilities, all described at a single point. This phenomenon is a defect in the coordinate system itself and cannot be remedied. Okay. So... the system simply fails at the specific point. One then says that while Cartesian coordinates cover map or chart all the three-dimensional space, cylindrical polar coordinates do not. exactly one point defies definition. Okay. Let's see. Coordinate systems in this regard can be thought of as a grid cover three-dimensional space. Three-dimensional space does not exactly one point define the coordinate system in regards to the thought of this grid covering three-dimensional space. The coordinate grid or map is infinite, smooth, and complete, while the polar one has a hole in the location of the origin. If one then wished to do a problem that studies the point as the origin uses a defect coordinate system, one has no choice but to shift the coordinate system itself such that the point in question no longer coincides with the origin. There's simply no way. This issue also further emphasizes that spatial points and coordinate maps are not the same thing. An obvious issue, perhaps, but one that is sometimes confused with the mind of beginners. That felt like it was just an over-explanation of things. But I'm guessing what they're saying is that because cylindrical coordinates are not really defined at the origin. Basically, there's literally like they said, a hole in the coordinate system. So it doesn't cover the whole space. That's what I managed to get from that, because like if the origin can be like any point within multiple points instead of 0, 0, 0, then practically you have something that's kind of like a problem in that case. Let's see, cylindrical coordinate grid, cylinder at a constant row, and the plane is constant. That looks pretty cool. Reminds me of like a building. I love how like mathematics can produce these beautiful pictures here. Let's see, remaining most commonly used system, the coordinates in 3 dimensions, is spherical coordinate systems. Yeah, this is the one that's a little bit more involved. Particularly useful in physics when problems exhibit spherical symmetry, as shown in figure 1.5, defines... Where is it? Here it is. So... I remember that you have to, like, remember these formulas here. So r is the radius, which is where the length of the vector, and then basically sine. So cosine is always going to go with I guess the quote-unquote x coordinate, and sine theta here. Let's see, it's also possible to define vectors by its polar coordinates, right? Oh, by cylindrical coordinates, okay. So rho plus z so these are when you're trying to convert cylindrical coordinates to spherical coordinates, or like vice versa. Let's see. Oh, it also suffers the same defect as coordinates. Once again, the point is so only if r is 0 and can be used while both are ambiguous. Okay, so it's two angles that are ambiguous in this case. That is very interesting, because obviously it's a point. It's not really a radius. It's practically like a little tiny point in space. Let's see, flat planes of coordinates of Cartesians, cylinders for cylindrical, or circles for polar, and spheres for spherical. We know here that these are not the only options. Other shapes can also be used. Let's see, sphere constant R and Q cones of constant theta. Complete spherical grid. Ooh, look how pretty that is. Oh, it's break time. Yeah, but you know, like, I think like reading this stuff is actually pretty fun. The book itself is pretty self-explanatory. I mean, it also brings up some interesting questions that I had to ask myself to basically wonder if I know enough about the subject, or at least know about the matter of like what it is that I have to understand about this subject matter. But I think like in math or in physics or anything involving like, you know, STEM, it requires a little bit of deep introspection. You have to ask like, I know this fact, but why is that? Or what is it that I can use to implement it in a way that would probably benefit someone's problem or benefit someone trying to make a revolutionary invention, you know, that type of stuff. But actually, like, for everyone in chat, like, you know, if it's your first time here and you love math or physics, or you just need something to keep yourself productive during, you know, maybe like you're procrastinating a bit and you need something to help, like, you know, get you into the mood to actually like work on the thing you want to work on, you know, if you're lurking in the chat, thank you for lurking. But if you want to keep up with, you know, the streams and just to be productive in your daily life, you know, drop a follow in Twitch, or if you're watching this on YouTube, you know, hit the like button, subscribe, and, you know, comment down below if you're watching this on YouTube. For all those that are joining us on YouTube, thank you guys for like giving the subs. I always appreciate it when people subscribe to the YouTube channel, because I don't multi-stream on YouTube because you know, like, I would have to worry about like how do I implement the chat to come together. I also have to worry about the like linking the streams together. I probably should ask like one of my other math streamer friends, Don, like how he multi-streams, because he multi-streams on both YouTube and Twitch. But for all those that are watching this on YouTube, like would you like me to like try to do multi-stream, like basically both Twitch and YouTube? You know, that's something I will take into consideration. Like if you want that, like put it in the comments down below, and I'll try to see if I can make that happen. Because usually the one thing I don't like about YouTube is that when it comes to streaming on YouTube, it's just a little bit more of a extra step that I feel like it shouldn't be there. Because like for me, it's like with Twitch, you just hit like you just have to have OBS and you just hit stream and you're automatically good to go. But with YouTube, I think you have to think about like what's the thumbnail. You have to think about setting up the description of what this whole thing is about, and you know, like it's a lot of setup just to basically just start streaming. And you know, the hardest thing for people, like especially content creators that want to do content creation or want to try to start content creating for the first time, they just want to hit the record of the stream button and that's it. Like they don't want to like go through this whole process of, you know, like some people like doing that. I don't like doing that. Like for me, it's just like I want to hit the stream button and let's go. That's basically what I usually like to do. But you know, like I love the fact that like there is like a, you know, a big math content creator community, especially for like Twitch, because you know, like I met a lot of people that are part of the math, I guess, / physics like Twitch community that basically like love to like teach people through streaming. And sometimes I feel like streaming might be like kind of like a new way of actually just engaging with the subject that you that you probably love, but you don't feel bombarded by like, you know, things like academia or like social pressures to basically say, I have this degree I'm working on, but I'm starting to lose track of the love of the subject that I have for the subject. You know, it's like people want to engage in the fun parts of the subject as well as the technical. And I think when you're in school, you just have to you focus on too much on the technical, but you end up wondering, it's like, why do I love this stuff? Like, what I feel like very bombarded by like all these assignments I have to do, or the way the professor's teaching the course, like I'm still not understanding it, and I feel as if like what is the technical knowledge I lack that I am not understanding, you know? It's like stuff like that, which are reasonable questions to ask, and you know, that brings people to doubt whether their love for mathematics or physics or both is like, do I have what it takes to actually be someone that can work in this field? And you know, and then the imposter syndrome comes in, and you start questioning your love for the subject. I know I have, especially when I started streaming this stuff, because I noticed that whenever I stream like math content for you guys, I have gotten problems wrong a lot, and I end up wondering is like, am I actually giving people like, you know, the math content that they deserve? Because I go from different subject to different subject, and I don't have really like a big structure. But I think when people go with a structure with math, they're so used to it because it's in a classroom. And sometimes like you learn a math topic, and if you love math, you have like a math topic that is in the back of your head that you want to learn. And then like if you hear like an idea that kind of unites the two, you end up wondering, is like, should I like investigate that? And then like you try to go on Google and you do your own education time. Basically you just look up stuff and try to see what is the thing that kind of brings the similarities of like the math subject you like to do and the math subject that you're learning. And then suddenly you find like something that unites them both in some way. Or maybe there's like nothing that unites them, but there's a similar concept that allows them to follow a similar formulation or pattern that basically you can implement. Because when people like do math, they just basically follow how the patterns behave, and sometimes those patterns are reflected in places that we never thought of before. But of course that's going into more applied mathematics, not really pure mathematics. I mean, pure mathematics, they probably have a lot of those because they don't have anything like, you know, they don't have to worry about things like the physical constants, or they don't have to worry about variables involving like economic models. They probably just have to worry about like, you know, does this mathematical parameter matches with this concept of like space in that regard. So it's like stuff like that. But like I said, I'm not a professional mathematician, or I'm not a graduate student that's studying this stuff. So if anyone has more experience in that, like I'm pretty sure you can explain it more eloquently. And if you would like to explain it in chat, you're more than happy to do so. Or if you're watching this on YouTube, you can put it down in the comments down below to basically like teach us what your experience has taught you about, like, you know, I guess what you've discovered on your math journey as well. And whether it be on the thing that you're working on, whether it be like just the idea you just thought up, or like a revelation that you came to while learning a subject that you probably weren't interested in it before. You know, because like sometimes we learn subjects that we don't want to learn, but at the same time it somehow collides with the thing that we really want to learn, you know. Hopefully I'm making sense. But you know, I feel as if like math is going to be an arduous journey, and physics is always going to be an arduous journey. Hopefully I'm using the word arduous right, but it feels as if like it's a journey that you have to constantly keep asking yourself. You think this stuff is cool, but at the same time it's like, do I have the tenacity to learn the technical details of the subject, and will that technical knowledge, will it be enough for me to actually say that I actually understand what this stuff is talking about? And you know, you keep questioning yourself about that all the time. Like, you end up asking, like, do I know enough technical knowledge to basically say I understand where this particular unsolved problem is or what it isn't, you know? And this is why, like, there's so many different specialists in academia that basically focus on particular problems. And these problems probably people wouldn't care about it because they're not related to like earning a certain profit or like making like a new machine. It's basically just a technical curiosity. And those technical curiosities can lead us to a far distance. Like, you know, like cryptography, for example. That all came from number theory. And like number theory, like I remember I think it was Jay Hardy that basically appreciated that number theory was probably the only math subject at the time that was viewed as sort of like very useless for applications, but it was so beautiful within the mathematical world. But eventually, like, we made computers, and cryptography was pioneered, and that's when number theory became very, very useful for applications for like the sciences. So, you know, math will eventually always find some application no matter how abstract it is. Now we have to think about, oh, what happens if we have knot theory? What application can we put with knot theory within actual like science or an actual STEM, you know? Like, I'm guessing knot theory will probably be involved with biology because it deals with like knots, and there's a lot of knots in human DNA. And if you're able to unravel like knots within human DNA, I think the story goes is that if you're able to unravel the knots that are tangled up in DNA, you would be able to at least like treat illnesses like cancer and stuff like more effectively. I'm not saying they're going to be cured. I'm just basically saying that because like DNA is like constantly being wrapped around and it's like being awfully like knotted, like if it was unfolded, maybe we would be able to like help ease people's like biological diseases like that may be inherited or probably just be produced because of like, you know, the way their body is kind of like structured. But that's just an idea, I think. Like I think I've read that in maybe like a science article, like a popular science article, like but I don't remember exactly where I got it from. After we have to keep in mind Hardy was a pacifist, right? During World War I think it was World War II, right? And a lot of applied mathematicians were used for ballistic computations, right? That's probably why he wasn't so thrilled about applied mathematics. That's fair. That's fair. I mean, physicists were not thrilled to the fact that they used applied physics to make, you know, the hydrogen bomb or the atomic bomb. So, you know, like, I understand where, like, you know, Hardy would come from if it's coming from that perspective. But, you know, with knowledge comes great responsibility. I mean, you can't stop the knowledge from coming out. That's why I think, like, with dang, like, why am I blanking out on his name? Shoot. The person that made the atomic bomb, I forgot what's his name. Like, I forgot how to pronounce it. There was literally a movie about him. Open. Dang, like I'm blanking out on the pronunciation now. Shoot. It'll probably come to me eventually. Yeah, like when the knowledge of the atomic bomb was like released, like many countries were starting to make them, and then like nuclear warheads became a big problem. And you end up wondering, like, as a human being, it's like we want to revolutionize people's ability to think and invent new things, but at the same time, like, how can you prevent that from, like, creating destruction in its path? Like, you know, like horrible destruction. Because the thing of it is that, like, the knowledge is out there, and, like, we can't really stop countries from, like, developing, like, you know, like, very destructive weapons for, like, warfare, unfortunately. I mean, I wish we could, but at the same time, I'm like, how do we stop them? We can't just stop the knowledge from getting out because it's already there. So what can you do at that point? And that's usually the hard part. That reminds me of the talk of Gudentech at CERN. Oh, what is that? What is that? Like, what was the talk about that? Was that basically the I guess when the public was afraid that black holes would come out from the Large Hadron Collider? I found it funny that CERN had to actually make an emergency pamphlet for that. Because it's like... It was about... Are we going to keep doing research in the future? Oh, okay. Okay, before we get into the next study session, guys, I will be right back. Just give me one quick second. Okay, guys, I'm back. So, let us get back to the book, shall we? Study timer is about to go on now. Alright, so... should we close this? Yeah, that makes it better. Okay. Ooh, this is something that I have not covered. Let's see, define systems. For example, consider the so-called elliptic spherical coordinates, where the surface of constant U defined concentric ecliptic cylinders, and surfaces of constant V or are hyperbolas, as shown in the figure 1.7. They are related to the Cartesian coordinates via... Oh, this is something I have not learned. Answer was a big no. That was around the time became a bit mad and isolated. Dang. Yeah, I think like when it comes to like knowledge, people will always seek out like, I guess, like the next knowledge, but like some of the older, like, I guess people that have more experience and they know where it's going, they'll be like, no, don't research this topic. You will find the answer, but you're not gonna like it, and it will lead to like implications that people will use. Okay, so let's see. Oh, it still uses Z as like the third coordinate. Like, no, okay, so we don't have to do conversions, okay. So A cosine U, so U is the centric ecliptic, okay, it's the surface constant. So that's basically the angle here, and V is supposed to be the surface of constant are hyperbolas. Oh, I've seen this picture before. So the constants u... Oh, okay. So the constants u are these. And the constants... Oh, okay. So basically these are the circles. And then the hyperbolas are here. Actually, like, when I was studying a little bit of, like, algebra, like, you know, just refreshing my mind on, like, basic math, I never really did, conic sections. I mean, I never fully delved deep into conic sections that much. Like, I mean, like, you know, like, the equations themselves, they look familiar to me, but at the same time, it's like, I don't remember, like, doing problems involving conic sections. Let's see, elliptic spherical coordinate grids in the XY plane, curves of a constant u, the ellipses. Oh, it's ellipses. My bad. Sorry, I didn't mean circles. I should have said ellipses. I'm correcting myself. So, let's see, the hyperbolas in... Okay, so v is the constant of the hyperbolas right here. And then z is 0. Okay. The extension of 3 dimensions is straightforward. Okay. The parabolic cylindrical coordinates grid in XY plane, parabolic curves of constant... How do you pronounce this Greek letter? And this Greek letter? You really start to understand conic sections when you learn about diagonalization in linear algebra. Oh, okay. So actually, maybe I'll just write that down, actually. Like, and probably I'll write it down for you guys, too. Oops. Something, I clicked something by accident on my other screen. So let's click here. Drag this down a little bit. So we'll just write what you just said, Sascha. So I think like the viewers on YouTube as well as the stream will appreciate it. So conic sections. We'll just put double arrows here, just to basically give a little bit symbolic mind map. Diagonalization. Linear algebra. Oops. Eraser. There we go. Back to pen. Algebra. Okay. That's a very classical application to diagonalization. Oh, okay. Are you talking about elliptic spherical coordinates? Like, are you saying that is the classic application to diagonalization? Sascha? Or is it something else that you're describing? Or just conic sections in general? Essentially, there is a correspondence between symmetric, just conic sections. Okay, so I'll just write that for. Okay, so the first thing you said is it's very okay. So I think we can just leave that there. And you also said symmetric. I don't know how all of these will come together for us, but at the same time, it's probably better for us to like write this knowledge down because Sascha is someone who's working on their masters. So I feel as if this will be like a creative like way of actually engaging with the math. It's like we're getting pieces of a puzzle that we don't know where the puzzle is, but maybe it will lead us somewhere. Who knows? We'll also write correspondence just to correspondence here. Yeah, I'm actually liking my handwriting on this application more. It looks much more clear and less scratchy. Oh, okay. Here are the equations here. This is parabolic sphere cylindrical coordinates. How do you pronounce this? How do you pronounce this? These Greek letters here. I want to make sure because I don't think I've heard professors pronounce these yet. At least for me. Let's see. The final example is parabolic coordinates. So they're still using U and V in this case. So the constants. Let's see. Parabolic spherical cylindrical coordinates grid in XY plane in the XY plane. Parabolic curves. Okay, the upright and the inverted. Oh, okay. So basically, it's just like the constants like that are like basically going down and up. Okay, that's very clear actually. Pretty much knowing the sign of the eigenvalue of the corresponding symmetric matrices. Classify your conic section up to linear change coordinates. Ooh, that's something that we can write down for you viewers at home. So, let's see. The sign of the eigenvalue. We don't know what it's going to mean for us, but at the same time, I feel as if it's good to basically just write this down. It might be like a thing that pops up as a I guess a thought bubble in our head whenever we think of more complicated subjects. Corresponding symmetric matrix. Classify your conic section up to linear change of coordinate. Okay, so we probably might have to learn eigenvalues. Correspond to a symmetric matrix. Classify your conic sections up to a linear change of coordinates. So I'm guessing basically based on the eigenvalue, when you say symmetric matrix, I'm guessing it's sort of like the same as like the inverse transformation matrix like we have here. And basically this allows you to, I guess, like see where the change is between the conic section way of actually looking at the coordinates compared to like say the linear way. Like that's what I'm trying to interpret. If I'm interpreting wrong, Sasha, let me know. What else did you send here? Okay, conic sections here. Because I think you also took a picture here. General. Yeah, here we go. General form of Cartesians. Let's see. Thank you for sending this, Sasha. Let's see what, because I'm actually looking at what you underlined. So what Sasha was talking about was this section, if you see my mouse. Like in Cartesian coordinate system, the graph of the quadratic equation in two variables is always a conic section, though it may be degenerate, and all conic sections arise in this way. The more general form, yeah, we've seen this before. You would see this in multivariable calculus. Let's see, matrix notation. Okay. Times x. Oh, okay. So you're basically doing both row and column vector. Interesting. E. Oh, okay. That's interesting how they write it. And oh, so then they all combine into like this thing. That's really, really cool. Yeah, that's pretty cool actually. I like it. Looks pretty interesting. So where were we? So in the top you have a general equation of conic sections. You can use the coefficient of the equation to build the matrix below. We usually want to work with 3x3 matrix. Remark, this is a symmetric matrix. Okay, yeah. Oh, okay. So a symmetric matrix is basically like it has to have the same number of rows and the same number of columns. Okay. Okay, that's what you mean. Okay, that's good to know. So going back, so you can use the coefficients of the equation to build the matrices below. So basically, these are the variables. So I'm guessing like these row vectors and this column vector, it has something to do with, okay, so we have X and Y here. So I'm guessing this is here because we have like this, we have like two like squares here of the two variables in addition to this middle term with both coordinates in there. I mean, that's my guess. That's my guess. What can we show is that the symmetric matrix is always has a real eigenvalues. Okay, so maybe we can write that down for all those at home that are like learning linear algebra. Maybe this will help you on your journey. So symmetric matrices always always has real eigenvalues. Symmetric here means that the matrix is symmetric along the diagonal. Oh, okay. Okay. Yeah, actually, Sasha, how do you pronounce these Greek letters? Like this and this? No. The one next to it. This one. Like, how do you pronounce those? Symmetric, we already read that. Another way of phrasing it is that it's equal to its transpose. Oh, okay. Let's see. All systems of coordinates we discuss and many others that exist are collectively known as orthogonal coordinate systems, i.e. perpendicular. In other words, their respective grid lines are perpendicular to each other at every point. There do exist non-orthogonal or skew coordinate systems. A simple example of which is given in the exercise. Exercise 1.1, use the computer, see if you can reproduce some of the coordinate grids in sections such as Fig 1.4, 1.7, 1.9. Once you had enough practice, plot and complete the grids for the following systems for numerical values of the given constants. You may wish to experiment with a few and see which ones give you the best plots. Chi and Nu? Okay. That's good to know. So basically the parabolic coordinate grid, the parabolical surfaces of constant V upright, and U inverted as shown, they can be thought of as the surface of revolution of the parabolic constants Chi and Nu, respectively. That looks like a pretty picture. I wonder, like, when design engineers, when they're designing this stuff, they have to know all different types of coordinate systems, especially if they want them to look very smooth and very well refined. Complete coordinate grids for the following systems and for numeral values of the given constraints. You may wish to experiment with a few of the best plots. Parabolical coordinates as defined. Where the constants A and B are set to. So mu is greater than A. Oh, these are the actual exercises. Where is the constant A, B set following limits on their coordinates? Very interesting. Actually, I haven't worked with what are these the hyperbolic, like, what was I gonna say? The hyperbolic trigonometric functions. I haven't really worked on those. Actually, like, it's funny because, like, my pre-calc class, we end up, like, learning the basic curves, but we never got into, like, more of the, I don't want to say the more exotic curves, but, like, the curves that you probably would learn, like, I think, like, involving more curved space surfaces. Let's see, measurements in the metric. So what does this exercise say? As an example of a non-orthogonal or skewed coordinates, consider a Cartesian coordinate system where the z-axis has been rotated in the yz plane by an angle alpha, as shown in the figure. Derive the transformation equation relating the original orthogonal xy and z coordinates to the skew coordinates x prime, y prime, and z prime. Ooh. The simplest possible example. So maybe to give you more context about how this section on coordinates is related to tensors. So right now we're just imagining mapping points to another point. What we'll do after that is learn about how we map vector to vector using those coordinates. Okay, so I'm guessing, like, you're just basically sending us up to basically you're basically telling us the roadmap that we're going on with this particular section of this book. Am I getting that right, Sascha? basically this is about setting up the spaces, like basically like the spaces we'll be working with, involving like, you know, if we have a vector that never changes, but it's always, its coordinates are gonna be intermingling with the different coordinate systems that we're given. That's what I'm guessing you're explaining to us in this case. So by vector here, you should think of them as direction. Right. But the vector itself doesn't change. It's just basically the coordinate systems change. Hey, Pen Center, how's it going? If you guys are not familiar with Pen Center, he is an awesome math streamer. And let me just shout you out. Pen Center. He was basically doing a stream today on linear algebra, also on vectors. So if you want to check out his math content, you're more than happy to do so. Give him a follow and keep up with what he puts out on the daily. He also does a lecture series on real analysis. I actually have to catch up with that. Luckily, he uploads stuff on YouTube too. So, you know, be sure to check out his content. He's an awesome person. In addition, much more mathematically enlightened than me. Yeah, we're just basically reading more on vectors. We're not really doing problems that much. I'm just basically trying to understand more on, like, you know, components and transformations and stuff. Although I do feel like I'm lacking when it comes to knowledge. We did write some notes, though. We did write some notes here, like quadravariant and covariant, like, you know. Like, I wrote, like, some of the ideas, and, like, Sasha also, like, gave us some ideas about, like, what we were reading about. So, basically, that's what we've been up to so far. Yeah, today is not really a problem day. It's more like read, be inspired day. And also, like, you know, I decided to put myself on camera, you know. Just to basically just, I have put myself on camera before when I streamed, not on this channel, but on my other channel. That was actually my default before, but then, like, my PC would sometimes, like, freeze my camera at times, because that was my old PC. My old PC would freeze up my camera if, like, there was too much graphic heavy stuff, so I kind of got annoyed, and that's when I started using a VTube model. But, you know, now I got a better PC, and it has a better graphics card, so I just thought, why not just come back to do camera once in a while, you know? Unfortunately, when we are working over R3, it's really easy to confuse points and vectors. Right, yeah. I get that, yeah. Congrats on the new PC. Yeah, I had it since last year, but, you know, like, my friend, one of my friends, like, built it for me. The one thing that we had to deal with was basically the power supply, because, my games would keep freezing, and we couldn't understand why I was freezing. And it took us, like, about, I think, 3 weeks to figure it out, because we didn't bother to take it to, back to the, to Micro Center to, like, have them check it out. Like, it probably could have been solved at that point, but, you know, like, he's, like, the stubborn type. He just basically had me play games to see when it would freeze or how it would freeze, and, like, what was the stats on my... It was just a lot of work for me to do. Let's see, linear transformations. But luckily we managed to figure it out, and basically when we changed the power supply, like, you know, all my games played fine, and, like, my PC was actually functioning fine, so we were over that debacle, and luckily it was before Christmas. I'm kind of glad that they actually put, like, actually I'll zoom in a little bit, and I think I'll just close that there so you guys can see the pages. I love the fact that Derek Flinch, I think that's his name. Let's see, title page. Yeah. Oh, Daniel Flinch. Daniel Flinch. Like, I love the fact that he basically goes into detail, but he also explains it in a very clear way. This, like, I think it took me a while to actually formulate this in my own words. Because I was like, okay, so this part, I think I had to basically formulate my own words. Like, basically, this is from the perspective of this coordinate system to this coordinate system. Because I would see this and I would be like, okay, how do I formulate this in my head to better remember this? So the question one has to ask himself is, how does change of coordinates map vector direction? How does change of coordinates are related to linear algebra? Ooh, we can probably write those questions down for you guys at home. Whether you're watching the stream on Twitch or whether you're watching this on YouTube after I've uploaded this, we could probably write those questions down. Those are probably going to be... And if you have answers to these questions, put them in the comments down below. Let's see. So... Okay, how does change of the coordinates map map vector direction, or map the vector direction? I probably should write that. The vector direction, question mark, and how does change of coordinates relate to linear algebra? Okay, some questions for you guys to ask yourselves at home. If you guys are studying linear algebra, it'll probably give you a bigger picture, and I'll probably think about it myself when I'm like off stream. Can you think what relates multivariable calculus to linear algebra? Yeah, I've been thinking about that, because the thing of it is that I remember when I was trying to do an engineering degree in college, when I tried to go back to school for the second time, I always thought that I should learn multivariable calculus and linear algebra like conjointly, because obviously like both of them seem to have a lot of relations. And plus, like, you learn some of the same stuff in linear algebra in multivariable calculus, like, you know, how the direction of the distance between like a plane and a line and all that stuff. So the relationship between multivariable calculus and linear algebra. I feel like, based on what I've read about tensors and like change of coordinate systems, I know when you do the change of coordinate systems, it can be related to the partial derivative. That's one thing I think I've learned from this book. It was somewhere in here. I remember it talked about partial derivatives as if you were to compare one coordinate system to another, you would use partial derivatives based on the original system, and then differentiate that with the difference between the new system that you're doing. That's the best way I can explain it out of my thoughts, but I don't know if that's the correct phrasing. As a matter of fact, you can't even state the definition of differential maps in several variables without linear algebra. Oh, okay. Let's see here. Yeah, I think it was like something like this, like you basically had to like differentiate and stuff. So actually, let's write down what you just said, Chaska. More notes. Whether they help, whether they lead us to a great discovery or not, we might as well just, you know, keep it in mind. say you need several wow, I can't even spell today. Variables to let's see, you can't even state the definition of a differential map in several variables without linear algebra. Oh, okay, so actually I should rewrite this differently. So linear algebra leads us to the definition of differentiable maps in multi-variable calculus. Okay. That's something I did not know. Interesting. So basically it leads to the definition of differentiable maps. What I'm guessing is that the differentiable maps are basically because functions map onto from the input to the output of a given function. But at this point, basically the differentiable maps, I'm guessing, are the differentiable functions in many variables. An important slogan to keep in mind is the differential maps are those that can be infinitesimal approximate by a linear map. Okay. Sasha is just basically dropping us a lot of knowledge today. I'm loving it. Oh. Thank you for the raid, Academy of Useless Ideas. How was your stream? Also, like, Pen Center, if you're still in chat, like, how was your stream as well? I will give you a shout out, Academy of Useless Ideas. So if you guys are not familiar with the Academy, they are also a math streamer. They love streaming like the deep complexities of math, but at the same time, they also are willing to explain it in a very, I would have to say, like, a clear, concise manner. Makes you feel smarter every time you check out their streams. So if you guys love math, be sure to check them out. I would have to say, like, if I feel like whenever I come into your streams, Academy, it feels as if, like, wow, I'm actually like in a sort of like a university lecture setting, which is not a bad thing because it makes me feel like I'm in the room with a lot of scholars. So what we were writing? Oh yeah. The slogan to keep in mind is that gotta write that. Differentiable maps are those that can be infinitesimally approximations by linear maps. Thank you, though. Everyone left my stream just before, so the party was just one. No, it's okay. It's okay. It's better to actually have, some people just drop in and just say hi. Welcome Raiders, welcome, welcome, welcome. I'm Peter, aka Math Spellbook. First time I'm putting the camera up, so you guys actually see my face for the first time, so, hopefully, that doesn't deter you. If you guys are so used to my VTube model, like if you want my YouTube, my VTube model back, I will put it back in the next stream. But if you don't mind, like, me presenting myself in this way, you can put it down in the comments below if you actually are watching this on YouTube, or, if you're in the Twitch chat, you can basically say that too. Whatever floats your boat. Let's see. As far as you don't get the PTSD due to my lecture, nah, it's fine. Yeah, I actually feel like I actually watch like some lectures on YouTube, like when it comes to like university courses. Sometimes like I get inspired by that, but then sometimes like I would listen to enough and then I would just basically watch something else. We often talk about philosophy and storytelling, so we have some breaks. That's good. That's good. You can always have a break for knowledge. You are just as cool as I imagine you. The camera and the background is cool. Oh, thank you. Thank you. I appreciate that. You're cool as well, Academy. Actually, like, all you guys, like, that know more math than me, which is, like, a lot of you, I'm like, dang, I'm surrounded by so many, like, talented and awesome people. Like, because, like, they have so much knowledge, and I want to be able to, like, live up to, getting up to that level. But at the same time, it's like the goals I have are pretty different, but at the same time, it's like, I don't even know the basics of math proofs. And I'm trying to learn math proofs on my own, which Sascha has told me. And if you guys don't know, Sascha is the Kellier cone, and basically what he told me is that learning proofs on your own is really, really hard because you don't have a professor to instruct you. And I'm like, yeah, that sounds about right. Yeah. Like, sometimes Monday you have to get the stuff done. Like, you gotta actually, like, do the hard stuff. So they go over a metric in this one. So we've done section 1 of this book. Well, we didn't do the problems, but we just read through it. Today's more like a reading day, because I just want to get inspired by the math right now. Like, doing the problems, I feel as if, like, if I understand, like, with examples, like, if I see examples, I'll be like, okay, I'll try this problem out and see how it goes. Let's see, partial derivatives. Yeah, because I know, like, with this book, they cover partial derivatives, which I was pretty surprised about. Once you understand the basics of yeah, and then basically you have to use derivatives to basically, like, kind of intertwine that with like other coordinate systems. I don't know how to yet, but at the same time, like, I'm quite familiar with partial derivatives. You don't have to be an instructor, but you have an army of math elites to help you. Right. Yeah, because, like, I know most of you guys are just into, like, mathematics, because I know Academy is more into, like, math is just basically a subject we just learn and get inspired by and just try to see the big picture of the mathematical world, or I guess the Platonic realm, as I would call it. For me, I just want to be able to learn not only about the Platonic realm of math, but also about how this Platonic realm of math is somehow seeped into the patterns of nature that we've come to know as the laws of physics. So a lot of the main theorem of multivariable calculus, like the chain rule, inverse function theorem, and implicit function theorem, are useful because they are hard. They turn hard problems from an analysis to linear algebra problems. Oh, okay. Let's write that down, actually. That's more knowledge we can use. Because the thing of it is with math, I get so stuck in the details that I'm like, yo, there's got to be a bigger picture here that I'm not looking at. Let's see. Main theorems of multivariable calculus. Okay, I thought it was like writing into part of the chat because I was gonna move this a little bit. Let's see. The chain rule. Inverse function theorem. So when it says the inverse function theorem, is that related to, like, say, the inverse transformation matrix? Do they have anything related to each other, or no? It's just a coincidence that one is called, that they're called like inverse. They are related? Okay, cool. See? Like, I know that basically there's gonna be some connection there. Like, there's gonna be some connection. Whether I know it mathematically or the details, it's like, you know, it's basically the first step. Are useful. So these things turn analytic analysis to linear algebra problems. That's pretty cool, actually. So a little thing that you guys can, like, if you guys are watching this on YouTube, like, more notes for you guys to actually use to apply your knowledge. Oh, more notes. Nice. Let's see. The inverse function theorem tells you differentiable. Actually, here's a question for you guys, since you guys are like higher up on math than me. Would you prefer learning linear algebra in conjunction with multivariable calculus, or would you rather learn linear algebra in conjunction with differential equations? Because I've seen books that done both, that one teaches like linear algebra with multivariable calculus, and another textbook teaches linear algebra with differential equations. Like, which I guess, like, collaboration of textbook would you choose to use? Because for me, I would rather learn linear algebra through along with multivariable calculus. Yeah, both sound fun. Right. Admit an inverse at least locally. So it doesn't work globally? If it's Jacobian matrix is invertible. What does that mean? Invertible. One way to concrete example is checking that polar coordinates are invertible just by checking the determinant of the Jacobian. No, because the differentiable just see in a small neighborhood of points. Oh, okay. So you can't integrate. So now I'm remembering that global, like something global, you would think of it as sort of more like an integral than a differentiable. Okay. Yeah, because like then I thought about it and I was like, oh, wait a minute. Derivatives mostly deal with like a very, very small section. I completely forgot about that. Okay. Yeah. Oh, we finished our second study session. Yeah, I know it wasn't like too much on problem solving today, guys, but I felt as if like we were able to like learn some new things, and thanks to Sasha, we learned a lot of things. and probably we learn some deep connections that, even though I know that I probably won't think about, like, I probably won't know exactly what the point of all this knowledge is until, like, maybe it somehow is related to something that's even bigger than I thought before. But, you know, it's, I thank you, Sasha, for sharing all your knowledge with us. It was, like, really, really, like, enjoyable to actually, like, see the knowledge you were sharing. If you want, we can do an example of polar coordinates after the break. How about this, Sasha? So, like, we can do that on tomorrow's stream if you like. Because, like, I feel like I have to review things like polar coordinates, hyperbolic, trig functions such as, like, was it sine h and, cosine h? Or cos? I forgot how you pronounce the new, the hyperbolic ones. But I feel like I actually have to do all those different coordinates, not coordinate systems, but those different types of, like, defining coordinate systems. And also conic sections. I also feel like I want to, like, get into our discussion about that too. Like, if you want, like, we basically can collab again, and you can give, like, us a knowledge drop on, like, you know, things related to, do you know about the trigonometric circle? The unit circle? Yes, I know about the unit circle. Or unless this is a different circle that I'm not thinking of. Because when you say trigonometric circle, I'm thinking, like, the circle you use for trigonometry. You should be more than able to do polar coordinate example. Yeah, it's just that, I feel as if, like, since you're relating it to linear algebra, like, if you, because I'm planning to, because I usually do, like, 2 study streams, and we just finished our last study stream. So, basically, like, after the break is over, we're probably gonna end stream there. And since, like, usually, like, whenever you explain stuff to us, I know you love to, like, give all the details, so, like, if you would like to, like, collab for tomorrow, like, I will present the board to you, and you can basically give us, a little bit of a lecture of what you know. Because I actually am curious about how the different coordinate systems, whether it be, the new ones that we learned, such as, what is it? Elliptical, cylindrical coordinates, in addition to parabolic coordinates, because I have not seen these coordinate systems before, and I feel like your knowledge with linear algebra should be able to, like, give us the spectrum of space, as it were. I can actually give that as the title for tomorrow's stream. If you want to share your knowledge with us, Sasha. It would be cool to see the Jacobian again. Yeah. I learned a little bit about it. I just haven't done problems involving it where I would just constantly practice at it. And also, for people that are more mathematically inclined than me, if you join our Discord server, you know, like, if you want to present me with math problems that you would like me to do on stream, and you gave me a list about what I need to study before actually attempting these problems, I'll be willing to do it, because, I feel as if, like, you guys have been, like, for people that have watched me for a while, I feel as if you guys are trying to engage on what type of student I am when it comes to math, and you guys know that I have a passion for it. So if you basically give me a problem and you tell me, like, oh, you need to study this, this, and this in order to understand this problem, I'd be willing to do that and put it on stream, and, you know, just learn from that problem. Like, any problem that makes me learn more about, like, you know, the intricacies of math, and if you do a math problem that's also related to a physics problem in some way that involves a lot of deeper math that you guys know, you can be sure to, like, present a problem to me. You can post it in, I think, in the same section that Sasha's been posting, stream material resources. You can basically post that in there if you would like to, because I think it would be very fun. Because I'm pretty sure that many of you guys that stream math, you guys are so used to, like, either doing problems by yourselves with math, or so used to like giving people lectures or like teaching people your knowledge in the field, or answering people's math questions. So if you guys want to present me with problems, I'd be more than happy to do them on stream, if you feel like I'm capable to. Because I feel as if, like with me, when I learn math, if I'm given the right instructor, like they basically tell me, okay, there's a lot to go over with this problem, but I need you to learn this, this, and this. And then if I'm given direction, then basically I just try to like learn as much as I can about it, and then I just apply it. So hey, happy Monday, Zach. How's it going? If you guys are not familiar with Zach, he is also a math streamer as well. So he is going for his PhD, and I think he's about to get his PhD, so we can't wait until that day comes. So give him a follow if you can. If you love math, why not give him a follow? He's gonna actually have his doctorate in I'm not sure what your thesis is, Zach, but you know, what was it that you were specializing in, actually? Because I think I missed the part when you actually were talking about the actual paper that you've been working on. I'll give a lowdown in May. Okay. Cool. Because I didn't know if you explained it during that time. It's real analysis qualifying exams. Oh, okay. Gotcha. Yeah, like with real analysis, I really have to work hard on that because proofs are not my strong suit. They're not my strong suit. And whenever I try to do a proof, I feel as if like, wow, I don't even know how to get started at all. I look at the problem and I'm like, oh, what do I need to do? Like, for me, like, I'm so used to computations, but I know with proofs, that's where the real magic happens. Especially with math. And if you know theoretical physics, I'm pretty sure that proof techniques will come in, like, handsomely when it comes to that. Pardon me, I'm just taking a cough drop. Because I love talking a lot when I'm with you guys, actually. I think I talk more on this stream than I do with my video game streams. I don't stream my video games here. I stream them on my other channel, my Uncle Talks channel. If you want to check that out, like, you know, basically I talk about, like, more than just math there. I basically just, like, talk to you guys, engage with you guys, and see how you're doing in life and all that stuff. As well as, like, probably get frustrated at games that I'm finding very difficult. Like, actually, I didn't start playing games until I got into Twitch. Like, at first, I would play a game called Mahjong Soul, which is basically just me playing Japanese Mahjong. That was with my, gaming channel. But, like, now that I basically, like, actually, for all those that are basically subscribed to my YouTube channel, I really appreciate it, because, when I see, like, I know I shouldn't concentrate on the numbers, but when I see you guys coming in and basically wanting to learn math or wanting to engage with me, even though I don't know as much math as, say, like, someone that's already in grad school or someone that's already in their undergraduate, I feel as if, like, wow, I'm actually bonding with people that want to learn as much as I do. Because, like, it surprises me how people, like, I know people have different perspectives and they have different ways of looking at life. But for me, it's like, I wonder why some people don't want to continue learning in life. They just want to get to a certain point and then they basically just get comfortable. But for me, it's like, I want to continuously learn stuff, and I always want to constantly have my mind blown by the new stuff that I've learned. It's not just math and physics that I'm also interested in. I'm also interested in, like, other languages like Japanese, Korean. Getting outside of that, I'm also interested in, like, how money works. So, you know, like, I'm into, like, personal finance and all that stuff. Of course, I don't give financial advice or anything because I'm still learning. You know, like, I try to, like, learn as much as I can from whatever things interest me. And I think that's what life is all about. But of course, it also depends on your personal values. Because some people value just wealth, and some people just, some people just value wealth, family, and basically stability. But like for me, it's like, you know, it varies. Like I value things like, you know, my freedom, my personal freedom, I mean, and like, you know, my ability to learn, my ability to be authentic to myself, you know, that sort of thing. Now, of course, like many people, like I'm pretty sure that many of us like have heard this before. It's like, oh, you know all this knowledge, but when are you gonna apply it so you can earn money and all that stuff? And I'm pretty sure some of us feel like defeated whenever we hear that, because it's like someone basically, like an office worker, like basically look at you and you're like a grad student and you're learning all this knowledge, but then they're like, if you're so smart, why aren't you rich? And then you're like, yeah, you got a point there. Yeah, it kind of sucks that people that are in academia, like, sometimes like they're like also acting as sort of like a starving artist, but instead of art, they're like in like this cycle of trying to figure out what the bigger truth is, and like it doesn't lead them to, I guess, like to a place where it feels like that their income is like worth like the pursuit of truth in that way. But of course the thing of it is that like it's also what you do with your funds and like your salary that also plays a part in that, you know. And of course, like Einstein, I think he also said that there's nothing like compound interest. So, you know, we gotta learn more than just like, you know, just like the stuff that we love to, unfortunately. But of course, like I'm just rambling on, but this is basically like how I am in real life. I basically just look at life like as if it's like this beautiful picture, and I try to see like, you know, when things go wrong, like people always blame each other because like this person did this or that person did that. But I try to look at it from a very broad perspective. It's like, oh, you thought one person has an interpretation that this is right, and one person thought that this interpretation is right. And you know, it drives not only conflict but also like friction. And I'm pretty sure like in the world, like a lot of people are just getting tired of that. And it's like, why can't we just work together and just like, you know, try to negotiate and try to like make sure things work out for, at least like for us, and for those that get left behind, we'll be compassionate and bring them back to wherever it is that they got lost, you know? Just basically like food for thought for myself, as well as how I feel about like, you know, the complexities of the world. But that will be all for today. I hope you guys enjoyed the stream. I know I did a lot of rambling, and I basically just did reading and like, you know, a little bit of note taking, but I hope you really enjoyed this the stream. In addition, or if you're watching this on YouTube, I hope you enjoyed watching the video. If you're watching this on YouTube, be sure to like, comment, and subscribe if you would like to tune in to more of my content. I will also post a link to my my Twitch channel and my Discord, as well as my my Uncle Talks channel where I play video games and stuff. So that will all be in the description down below. But if you're in my Twitch chat right now, like, you know, I'm pretty sure my YouTube channel has already been posted by the bot. Yes, it has. And I've also posted my Uncle Talks channel over there. So, and I will post my Discord into the chat as well. So anyone lurking, thank you for lurking. If you want a productive stream to keep yourself productive on whatever studies or, you know, projects you're doing on your computer, you can turn me on the background, and then basically like you can just feel like you're being productive on the thing that you really want to do, or you really want to get done, because you know it will better yourself as a person, or, you know, improve like your work ethic or whatever. But whatever it is that you're trying to do the project for, hopefully I was able to help you feel like you're in a space that makes you feel more productive. Okay, I think that will do it for today, guys. Thank you for joining me today, and always remember, everyone is precious. You guys are just as precious as everyone else. And I guess I will see you guys tomorrow. So take care, guys. Bye-bye.